So, hi everyone. My name is Rob Canzaneri, and I would like to thank Kenny Neal for being the co-leader chapter. And I welcome everyone to the Data Architecture Virtual Chapter. Um, Today, we're going to do something really special. We're going to give out 2 gift cards because last month we had to cancel due to, the speaker had some personal things and we had to cancel. But we have that speaker rescheduled for March, so which is great. But today we have Kevin Kline, and I'm so excited about this, and he's going to be talking to us. So Kevin actually can hear me, so thank you, Kevin, for coming today.
Oh, my pleasure.
If y'all ever have questions or want to speak at this webinar, you can email me. I'm Rob at SQLtigers.com. Just send me an email, and we'll let you speak. And we appreciate sharing great SQL knowledge to the community. That's what it's really all about. Let's go to the next screen. All right, there we go. So Nutanix is a great partner with us. They're going to allow us to give out actually today 2 $100 gift cards to y'all. So if check your junk mail, you may be a lucky winner. But thank you, Nutanix, for being our sponsor and making these webinars possible. If you have time, click on check out the link, the bit.ly link. I know they really appreciate it when y'all sign in and check out what their products are. And they always, they speak highly of our group, and they're very nice to sponsor us. So next month, Nutanix is going to give a speech, talk on a topic. We don't know yet, to be determined. And then we have in March, Kimberly's going to give an optimizing store procedure talk. So that's going to be a great talk too. So if you have time, sign up, and we'll look forward to having y'all join us again. So PASS is really a neat organization, and they're going to have a marathon, and it's on Linux, December the 13th, which is coming up. So, go ahead and log into the PASS website and sign up. I'm probably going to do this. I like to see what this is about too. Upcoming other sessions on the marathon, you can see there are quite a few. Here. If you didn't have a chance to go to Summit this year, they're going to have, you can get the recordings. So you go to PASS Boutique and order the recordings. And here are some upcoming webinars. It's kind of cool the way the virtual chapters do this. They have different webinars, have different people, and they talk, and it's all free. So I highly encourage anyone that wants to learn more about SQL or some of these topics, just go to the PASS website and sign up. Here are a few more coming up. And like I was mentioning, there's a lot of groups. So there's always something to be interested in, PowerShell or performance or big data. It's just amazing how many groups there are, even Russian. So upcoming SQL Saturdays. So here are some SQL Saturdays coming up. And if you're in the U.S. and Washington, well, let's see the date. Yeah, you can check out these, sign up for these SQL Saturdays coming up. And, oh, yeah, the website is SQLSaturday.com. So log in and you keep up to what's going on. So with that, I'm going to turn it over to Kevin.
All right.
Let's see. We're going to try and get this going here. Here we go.
All right. Let's show my screen here. If I can get that worked out right. Okay. So everyone, thanks so much for carving out some time to spend it with me today. I'm coming to you from Nashville, Tennessee, where I believe it is considerably colder. It was about 32 degrees this morning and actually looked like winter. So you guys have the good fortune to be in a little bit warmer climate. So, I've never spoken for this virtual chapter before. I've spoken for a lot of them, as well as a lot of user groups and things like that over the years, but never spoken for this one before. And one thing that would be really nice to see would be, let me know, if you don't mind taking a moment in the chat window and just letting me know what your title is. I'm curious if everybody is a developer, or maybe you're a DBA or an analyst or something like that. So it'd be good to know, those of you who are thinking a lot about architecture, what sort of job you're working. But today we're going to talk about data design, basically, database design, architectural choices with regards to database design, and some of the uncommon things, or the lesser known things that impact performance. And the idea is stuff that, you've created tables and done things like that, but you might not realize that some of those choices have really big implications for how things are going to perform. So just a quick word from my company, Century One. We make the best of breed, kind of the premier monitoring, performance tuning, and alerting products for SQL Server. Our best known product is called SQL Sentry, but we also do monitoring products and alerting products for Windows, for virtualization, for analysis services, and everything in the cloud as well. We also do a really popular product that it's so free we don't even ask for an email address, and that product is called Plan Explorer. So if you ever have tuned queries and you're not using Plan Explorer, you're missing out. This tool is fantastic, and it will make your life a lot easier. We are very, very engaged in the community. We have a great blog at SQLperformance.com, videos at SQLcentury.tv, so I've got probably 12 hours of query tuning videos up there. I'm actually, as soon as I'm done here, I'm going to write a blog post at blogs.century1.com, where you'll be able to get the slides as well as all the scripts that I'm going to show today. And one of our most popular offerings is our free ebooks. Well, they're free for you. Normally they're $10 on the Amazon Kindle bookstore, but if you go to this URL, then we have these 5 ebooks. Actually, we have 2 new ones that I'm not quite sure if they're available from that same link there. But each of these are normally $10 in the Kindle bookstore, and online, filling out the paperwork there, you can get them for free, and they're not little 30-page, chapter-sized pamphlets or kind of throwaway stuff like that. The shortest of them is over 320-something pages long, and they're full of articles written by the best in the business, people like Aaron Bertrand and Paul Randall and Jonathan Kahaya, some of the MVPs, Microsoft celebrities, the luminaries of our industry. So it's definitely worth your time. All right, so let's dive into the presentation. Just a quick note about myself, Kevin Kline. I am a principal program manager at Century One. I've been a Microsoft Most Valuable Professional since 2003, and I answer all questions. I don't always know the answer to your question, but if you send me an email, I know someone who knows the answer to your question. I've been using SQL Server since before it was a Windows product. I was 6 years on Oracle before that. So there was a long period of time, all the 90s basically, when I knew everyone on the Microsoft SQL Server dev team. I'd love to get connected with you on LinkedIn and Twitter and Facebook. So all of those are actually KE Kline, so you can hit me up there. Started my career back in the 80s as an Oracle person working for NASA in Huntsville, Alabama at the Marshall Space Flight Center. And I went on to a big consulting and accounting company, really large one, and was one of the founders of PASS. And I was the president of PASS for 4 years in the early 2000s, got that organization up and running. And I've written many books, 11 books. My best known one in the industry is SQL in a Nutshell. Still a very popular book, and was a bestseller. So what are we going to talk about today? Well, we've already had our introductions, and I'm going to go fast through these 10 different topics because there's a lot to cover. In fact, quite a few of these really could be their own full day class, or maybe their own 1 hour session each. But I'm going to give you a lot of information about how to design databases on SQL Server and different considerations to keep in mind. I won't necessarily go into every detail and every aspect of all of these different things, but each of these represent kind of some hard lessons learned that I've had in my long career, where you do some of these things wrong, and 6 months, a year after you launch a big application, which the company really depends on now, you're stuck because you didn't design it right from the beginning. By the way, and just as an aside, a lot of people have really latched on to some of these so-called NoSQL databases. That's actually an acronym. It stands for Not Only SQL. And one of the appeals of NoSQL databases is that they purport to not need as much design at the beginning. They have a design philosophy called schema on extraction rather than schema on creation. And the truth is that that's not true. They do allow you to do that, but just like relational databases, if you don't design it well from the beginning, you're not going to perform well. So just thought I'd throw that out as a little tidbit. So if you're thinking about switching to Hadoop or MongoDB or Cassandra or something like that, beware. They can be very high performance, but so can relational databases. All right, so let's jump in. So one of the things that I want to start with, because we're going to come back to this, is the basic fundamental building blocks of a database. And we're going to design for those building blocks. And the first and most important thing to remember around our three primary structures, that is tables without a clustered index, those are called heaps. Tables with a clustered index, so we'll just call them clustered tables. And then non-clustered indexes, right? And all three of those are built upon an 8K data page, okay? And I've run into people who say, oh, I didn't realize indexes used 8K data pages too. Yep, they all do. And an 8K data page looks kind of like this little box here on the screen. Up at the top, what we've got is a page header. And that page header contains all kinds of very important information, okay? It's going to have things like the page ID. It's going to have the next page ID, the previous page ID. It's got a little spot in there to tell how much of the space is free. It's got an ID for the object that owns it. It's got other little things too. For example, it's got a little bit in there that tells if it's a dirty page or a clean page. It's got a bit in there in this little header that tells whether it has been subjected to a full backup since data on that page has changed. And that, if you've ever used a differential backup, which can go really, really fast, then one of the things about it is that all it has to do is look at that one little bit in the header of all the pages, and SQL Server will actually back up that entire page very, very quickly. And that's how it's able to make those differential backups go so quickly. It's right there. It's one little spot, same place every time, super fast. Important stuff there, but most of us don't need to know about it. The other thing too about this page header is that it is 96 bytes in total. So the amount of free space that you have available on a page is 8,096 bytes, okay? That's the total amount that you've got. Now at the very end, there's a little spot as well called a slot array. And the slot array keeps logical track of the records that are appearing on that page. Now SQL Server handles all of that by itself without you having to look at it or manage it or understand it even when it's handling all of the non-clustered indexes. But for regular data tables, it kind of makes sense when you insert the different records in there of, let's say, people and their names and things like that. Then what that slot array does is it just flips a little bit so that SQL Server knows exactly where those records appear in the list. And so if for some reason one of the record values is different, and then something else changes later on, then you can see in that slot array where to find everything, right? So that fifth record that was inserted has an ID of 4, but the slot array tells SQL Server that it's the fifth one in that page, okay? And again, this is important because SQL Server is going to try to get as much work done within a page as it can, and then it does other things that might span multiple pages, and so that can provoke situations where there's extra I/O, and I'm going to go into some more detail on that in just a second. Okay, so let's talk about heaps versus clustered indexes. And this is kind of elementary information. I'm betting that the majority of you understand this, but it's possible that this is new to some of us. So I'll just dive into this just to make sure we all get it. When we have a heap, that is a table that does not have a clustered index, it basically has one organizing component, and that is an index allocation map. And those appear about every 4 gigabytes or so. And SQL Server uses index allocation maps in another structure. You don't need to remember this, but it uses these things called IAMs and PFS, a page free space file, so that it can find where to put the next record. But like it says, it's a heap. There's just no organization whatsoever in this. So that means all records are just thrown in there willy-nilly. And if you need to select information out of that, then SQL Server always has to do a scan. It has to read all the different pages in order to get its work done. So it's not able to do anything really quickly if it has a ton of data in there. It's really inefficient for transaction processing. And in fact, that's one of the one of the best practices of building SQL Server tables, is that if you're going to use this for much of anything, then you definitely want to put a clustered index on there. But it is efficient for a few things. Namely, if you are going to build out, let's say, a really, really big data load. So you've got 12 million records that come from all across the world every weekend from all the different stores that this retail operation has, and they need to be loaded into one table. You want to do that as quickly as you can. Then a heap is not a bad way to do that. And then once you've got that heap set up, you can turn around and pump that data into another table, organize it, index it, sort it with a clustered index, and that sort of thing. There are some overhead elements to this. A heap has something called a RID, a row ID, and that's an extra 8 bytes. And the row ID is laid out in such a way that it tells you what the file is, the page is, and the specific slot for all the different records that are in there. And this sometimes becomes important for something called a forwarded record pointer. And so I'm pointing here at the screen. Imagine if you had a situation where you had a record that spanned 2 pages. The record itself was actually 14K. So it didn't start on the IAM. That's a page set aside for this, but it started on page 2 and it bled over onto page 3. And then because of fragmentation and so forth, page 3 appeared way back here sequentially. Well, SQL Server doesn't have any means of finding the first part of the record on this page and the next part of the record way down here. So it basically, and I'm kind of oversimplifying, but it creates something called a forwarded record pointer, which is like a pseudo clustered key. And so one of the things I always encourage people to look for in your databases is if you had a forward records per second perfmon counter rating greater than 1. If you do, then you know that you've got heaps in your user database that are impacting performance, right? So that's one example of how that can be a pretty important problem. All right, so having said that, that's not the structure most of us are going to use. Most of us are going to use a clustered index sorted table. And so what we have there with a clustered index is we start with a heap, we create our clustered index, and what it does is it sorts all of this lowest level of data on the leaf pages And it creates between each page something called a doubly linked list. So this way SQL Server can tell very easily where one page starts and the other, where it starts, where it ends, and where the next one picks up. So in that case of a single record that was 14K in size and it actually had to span 2 pages, Clustered Index can handle that very easily because of the doubly linked list. It'll tell it exactly where one is and begins and the other ends. And what SQL Server does is it actually uses what's called a balanced tree structure. A lot of people have heard of it called a B tree, but it doesn't stand for binary. It stands for balanced tree structure. And what it does is it creates these intermediate pages, and there could be many levels of them. And I've just got a simple example here that goes from a root page, and you can see it's kind of like an upside down tree. That's why they call these leaf pages. It starts at the root, and it goes down to all the leaf levels. So where with the heap, if we wanted to look up one record, it would have to scan that entire table. With a clustered index page, we could say to SQL Server, hey, I need to find everybody whose last name is Baxter. And so what happens is with the balance tree at the root, it says, okay, everything from A to M goes to the left, everything from N to Z goes to the right. It's balanced, right? So you either go left or right, and then it gets to the left and it says, okay, everybody A through B goes to page 1. Everything that starts with B, A through C goes to page 2. Everything that is C through D goes to this page. And so instead of reading all the pages in the table, SQL Server is able to read only 3 8K pages to execute your entire operation and thereby be a heck of a lot faster. Now, then on top of that, we can throw in non-clustered indexes. And non-clustered indexes are also constructed of 8K data pages, right? In the same way. So again, we do have this root node, this that is similar to what we have over there on the on the clustered index. And then we have one or many layers, again, intermediate pages, leaf pages of the indexes for the non-clustered indexes here. Except that these, instead of pointing directly to the data where it resides, these actually are pointers to where it can find the data that it needs on the leaf pages of the clustered index. And you can have non-clustered indexes on both clustered indexes and on, whoops, went the wrong way on my slides. You can have them on clustered indexes and on heaps. A lot of people don't realize you can put non-clustered indexes on those. So in either case, you can point to those. It's just like the index in the back of a book, where it's topical rather than kind of the table of contents in the front, which is sequential. So that table of contents in the front being sequential, that is like the clustered index here. It is the physical sort order of the data. Whereas the non-clustered index doesn't go in physical sort order, it goes in topic order. So if this was about employees, you might have a non-clustered index on hire dates, or you might have a non-clustered index on home address or something like that, so that those can be looked up much, much quicker, okay? Now, it's always going to have at least one more intermediate level, by the way, than the clustered index. And I have mentioned that it can be applied to a heap. Yes, it can be applied to a heap, but it's sure not nearly as valuable or an efficient of a page of a performance boost as having it on a clustered table. So your mileage may vary if you have to use heaps a lot. I hope you don't. So that's kind of the basics, but now let's dive into a little bit more detail. And one of the first things is when we choose to build clustered indexes, what should we choose? And one of the really bad recommendations that we see out there a lot is to build your clustered indexes on GUIDs. And this is actually bad idea, really bad idea. Now, if for no other reason, I'm going to point out the troubleshooting down here at the bottom, okay? I'm just the kind of person who likes to, let's minimize the fuss. Troubleshooting a GUID, I mean, look at this value. No human being can hold this in their brain. Whereas if our clustered index is built on a monotonically increasing integer value or a big int, let's say, if I have to figure out why order 42 or 42,000 isn't processing properly, that's a heck of a lot easier on my brain to figure out. Sequential GUIDs are not so bad either. I mean, they are just really big, right? But they are going to be just a massive number, and they increase, numerically like that. The biggest problem with GUIDs, there's two huge problems with GUIDs. The first is they create page splits like you won't believe, probably 50 to 70, 80% more than the exact same table structure in an OLTP application, not in a BI application. But in the transaction processing system, they'll have 50, 80, 100% more page splits than the exact same thing that's built around an integer or a big int. Again, sequential GUIDs pretty much get rid of that problem. The other thing that they cause is just ridiculously bad fragmentation. I'm talking 99.998327% fragmentation. So it is a really, really problematic situation for I/O. If you're running on disks, particularly, it's going to be terrible performance. If you have SSDs, it may not be terrible, but it's still, like I said, just massive amounts more I/O than you really need. So maybe you can get away from that by getting away from GUIDs. And you might be saying to yourself, no problem, we don't use that. You may not design with that, but if you do use ORMs like Entity Framework, or you use maybe in Hibernate or something like that, those use GUIDs everywhere. Every primary key clustered index is going to be a GUID. So you're going to have these problems like crazy, okay? Now, one other thing that goes along with this is that GUIDs are really big. I say wide here, but they consume a lot of space. And that space gets used up, not just on disk, that space gets used in memory as well, okay? And so, memory still, even if you've got a huge, massive SAN, memory is still expensive. And so you could be using up a lot more than you want to. It takes 16 bytes, whereas an int is only is a much smaller amount, only about 4. Interesting story, an example of poor clustering index choices. Had a situation where a client chose a unique identifier, as you would use it when you define your table, and they chose it because it was beneficial to their .NET environment. But they're expensive pointers because they're, as I mentioned, they're not sequential, they're globally unique, and because they consume that 16 bytes, they're quite big. But when you've got when you've got dozens of billions of rows, and it's fragmenting like crazy. In this case, a real world case, 99.998% fragmented. Over 100 gigabytes of disk space were being wasted. And anytime they wanted to load things into memory, it also was wasting gigabytes of memory at a time because of the fragmentation and so forth. So just switching over to an identity enabled them to get away from that. And it also reduced some other problems that were happening in there associated with GUIDs, such as some foreign key issues that they were having. So it's really kind of something that a lot of people don't realize, that GUIDs can be hurting your performance. Now, I mentioned that GUIDs take up a lot of space, but I see all kinds of situations in which nobody working on this particular database is paying attention to the idea of how full their 8K data pages are. So they have declared a table that's got 32 columns, and all the columns are varchar 2000, something like that. And that's, that's kind of ridiculous. If all of those columns get used at one time, you're going to have rows in your table that are, many hundreds of Ks in size, maybe megabytes in size. So I always encourage people when they're designing their database to take a look at the data consumption of each of the different columns, and that's the declared amount that you have set out. There's some tables in the Microsoft documentation that tell you how much everything consumes, and figure out, well, this is an int, it's 4 bytes. This is, but it's nullable, so that has some overhead to it, and then we have a character 5, and so that's going to consume 5 bytes. It's not null. We have varchar 30, and so add all of that up, and then divide that number that you get, which is for the row size, and divide that by 8096, and you'll see how many pages you can fit on a single row. And then think about the way your database is designed to work. And if your database can only fit 3 rows per page, or I'm sorry, your table can only fit 3 rows per page, and you plan on doing hundreds of thousands or millions of read operations at a time, you might want to try and re-architect this a little bit, redesign it, because you're going to be reading, you're going to be doing thousands and thousands, hundreds of thousands of IOPS. I especially make this a top priority for max data types. There are some big issues with max data types. As I mentioned, if you have max allows unlimited amount of data to be put into a table. So if it's bigger than the single 8K data page can hold and it's a heap, then you're going to have that forwarded record pointer problem that I mentioned. But also max data types provoke something called an implicit conversion whenever you compare that max data type against other of the same data type that aren't max. So let's say you had a varchar max in one column and a varchar 500 in another column. They were both comment columns, right? The varchar max won't be able to execute a normal search argument. It won't be able to use the index, in other words, because it's got this implicit conversion, because one is varchar max and the other is varchar 500. That's a really big problem. Another thing, again, like I said, I see developers in particular like, well, let's just have one big table. Lots and lots of columns in there, all pointing to one primary key. And that usually begs a deeper analysis, that the table is in first normal form or maybe second normal form. And that is going to cause all kinds of, it's going to cause some data problems, but it's also going to cause a lot of it will cause some small performance problems, but it'll also cause lots and lots of data quality problems, which I actually will cover in a little bit more detail later on. I also see problems where we have redundant data, appearing multiple times in a table, or we have malformed data, which is kind of funny because you'll see that show up in a situation in which every time a particular column is referenced in a query or a stored procedure, what you see is that it always has a calculation being executed on it, or you'll see that it's always being referenced with a date part function, and or it's being concatenated to a group of other values. And if you're doing that, again, you have the same problem that the max data types has, which anytime you make a function call on a column that has an index, SQL Server can't use the index. And so if you're doing date part function calls on a date column, and you're thinking, oh, it should be easy for it to find the most recent records for the last 30 days because we're indexing that. No, it won't be, because whenever you put that function call on it, it now moves from deterministic values to non-deterministic, and so SQL Server can't use it. Another really, really common problem that we see is called column stuffing. And that's where they declare, the designers declare, let's say, a particular column to be, let's say, varchar 2000 or varchar max. And then they just stuff comma separated values into it, or XML or JSON values. And then they have to spend all this time parsing the data, shredding it when it comes out, or validating when it goes in, and writing these big, massive stored procedures. And that is extremely cumbersome. So it's the kind of thing that you really want to keep an eye on. Aaron Bertrand, and I have some notes in the in the slide deck notes. Aaron Bertrand has some really good ways to handle this. If you have built a system around column stuffing, it's pretty common. So there's some things you can do to fix or improve performance. And this is one area where more recent versions of SQL Server perform enormously better than the older ones. So if you're running on SQL Server 2008 or 2008 R2, and you upgrade to a newer version, you're going to get a lot better performance out of your XML, for example. Now, just another note on clustered indexes. If possible, you want to make them narrow, static in the sense that they won't change once you've created those values, unique, and I'm going to go into some more detail on that, and monotonically increasing. You know, it's an increasing number that goes up over time. One reason why we want it to be narrow is because the clustered index key has to appear in every data page, in every record of the non-clustered indexes. So every non-clustered index you have has to have the clustered index in it, so it can find, you know, it's a pointer to the different rows in the clustered index. So that means if you have a surrogate key, if you have a natural key that's composed of several different elements, let's say first name, last name, date of birth, and social security number, all four of those together have to appear in your non-clustered index. So that means your non-clustered index, and you might have a dozen of them, right? Or 2 dozen of them in a really big table. It's going to cause an enormous amount of bloat, as opposed to if you had a employee ID that was just a monotonically increasing number, and that's very narrow. You know, let's just say it's an integer, for example. That wouldn't take up much space at all in all the other non-clustered indexes. Static is important because if these ever change, all of the pointers in all of the non-clustered indexes also have to be updated. And so that can create a lot of additional work downstream. Finally, just to throw this one out, unique. A lot of people don't realize that you can create a clustered index that's not unique. It's part of the default, but you can turn it off. But if you do turn it off, SQL Server actually has to incur some extra overhead to deal with that. And that's because it's a 4-byte uniqueifier that it has to add to every clustered index key. And because that uniqueifier is stored as if it was a varchar, a variable length column, variable length columns also have a little bit of overhead on them. In fact, it's another total of 8 bytes of overhead space. It's only 6 bytes of overhead if you have other varchars in the table. But if this is the only one that's a varchar, it adds another 8 overhead altogether. So it can be really, really significant. So that's why I encourage you to, another reason why I encourage you to go with that int or big int set of values. Okay? Now, another thing that a lot of people have heard of, maybe you haven't, is something called page splits. This is a really big deal. When we create our indexes, both clustered indexes and non-clustered indexes, when we create them or we rebuild them, SQL Server goes through and makes sure that the indexes are 100% full, and that there's no empty space left on the leaf or the intermediate pages. Okay, that the default value is 0 or is the same as 100. That means fill up each of these pages 100% full. And you do actually want your tables to be 100% full in read-heavy or read-only applications like a BI situation. That's because the more pages we can completely fill up, that means the less pages we might potentially have to read during a big I/O operation. And so we want that to happen if we're in a BI app that's reading millions of records at a time. So we want that there. But in an OLTP application, not so much. And the reason for that is these page splits. So let's say I've got 100% full down here on the leaf pages, and then someone comes along and inserts a record, and that, or it could be an update. They update a record and they add a comment where there was no comment before to that record, but the page is already full. So what SQL Server has to do is it has to take half of the data from that page and it moves it to an entirely new page. It's called splitting that page. It takes 50% of the records, basically, all the records from the point at which that page split occurred, moves half of them over to the new page. The thing is about that page split is that it's not wedged in here. It's wedged into the first open spot it can find anywhere on the database file. So now we've got a situation in which there's fragmentation, right? And that's why GUIDs cause enormous amounts of fragmentation, because they always fill up and spill over and fill up and spill over and fill up and spill over. But we can actually do that to ourselves based on the way we design our tables, that we have lots of page splits because of the clustered index we chose, because a lot of the values are default at first, are empty at first, and then they get added to later on or expanded later on. And so it's the kind of thing you need to come back and rebuild your indexes after the fact. Now, when you do that, you may even have situations where you've got so much pressure on your indexes, even not just on the data pages, but you're having page splits happen up on your intermediate pages here. And if that happens, and I've been tuning SQL servers for a long, long time, and that's only happened to me in one application in all these 20-something years. But if that does happen, then you can use the fill factor setting when you rebuild your indexes or when you create them, or you can also use an alter table statement to do it now. And you can also use the pad index option. And what that will do is you could say with a fill factor, let's say of 80, that's my usual default on transaction processing systems. I say, if it is going to be used heavily for transaction processing, and so I leave 20% free on each of these data pages. Now that does mean that I'm wasting a little bit of space. And so if I'm doing long reads, across an entire table, well, I'm doing 20% more than I might want to. But what that means is I have much less overhead from all the inserts and updates that are happening. And again, every time I do writes, that means I also have to update all of the non-clustered indexes as well, so that they keep up with all the proper pointers. So it's important to, the more indexes you have on the table, non-clustered indexes you have on the table, the more likely it is that page split is going to cause cascading amounts of I/O, because it doesn't just cause the first page split to move the data around, it also causes all this other work happening in the non-clustered indexes. Now, I mentioned how, if you have a clustered index that has multiple columns in it, that can cause some issues because it's really, really wide. It's big, right? There are some other things too that indexes that are concatenated can cause. The biggest thing to remember is that anytime you have a concatenated index, also called a compound key, I've also heard it called a composite key, anytime you've got an index that is multiple columns, like in this case, let's say I've got a yellow pages and it's got the last name and the first name and the street address, but that's actually what the primary key clustered index is. SQL Server has to address these columns in ordinal position to be able to make use of that column. So let's say in this yellow pages table, I haven't created an index on street, all right? So if I just have that index on that clustered index, it'll work great if I have a query that looks at last name. It'll work great if I look at last name and first name. In both cases, if I go all the way down to street, that'll work great. But what if I have where it's first name or something else? Even though, again, if we look back, even though first name is part of this index, SQL Server won't be able to use that clustered key or even a non-clustered index to find this. We'd have to have a separate index altogether to find that first name, or separate index altogether to find the street, right? So it's a really important thing to do to make sure that that you take advantage of the ordinal position where it's appropriate, okay? What a lot of people do is instead of using those ordinal position sort of multiple column keys, is they'll use a surrogate key. They'll create either an identity column, integer identity column, or something like that, a sequential ID, and they'll call that Yellow Pages ID, and that'll be the primary key and the clustered index. But then they'll also have another key on last name, first name, and street. So that's the typical workaround there. Now, I have a little note here, and I don't have time to go into it, but if you want to take a look at the hidden slides, I talk about the transitive properties. You might remember that from algebra. If A equals B and B equals C, that means that C equals A, right? So sometimes you've got a situation in which you're doing a join across multiple tables, where employee ID first name equals Yellow Pages first name, and Yellow Pages first name equals, customer first name. If you don't go in and actually tell SQL Server and customer first name equals employee first name, it'll actually lose out on a bunch of different optimizer choices and won't perform as well as if you added in that last A equals C condition in your join there. So just a quick little note there. Now, unfortunately, I don't have time to talk to all of these, but these are problems that I see all the time, like with data type choices. For example, some really illogical data types. We see people using strings, like a char or varchar, or numeric data types to keep track of dates or times. We'll see places where people use time when what they really want is an interval. And so all kinds of hijinks ensue because they have to do math calculations all the time. We'll see people use money or float because they sound appropriate, but they're actually not, because they don't need precision. And so anytime they have those data types that have precision, they're no longer directly compatible with integer data types. We see people use timestamp all the time because they think it involves date and time, when in fact it doesn't. And then there's this one which none of us know why it's in here, SQL variant. Don't use it. It's not a good data type. We've also got a lot of data types that waste a lot of space, or data type choices. For example, we see people use date time when small date time, or even just date would work as well. We see people use int or big int when you could use tiny int or small, and it's going to save you a large number of bytes. We see people use character data type, or char or nchar when varchar would be better. Varchar does have one extra byte for overhead to let them know if there's anything in there at all. But once you've cleared that out of the way, it's basically going to save you space, because with a char, it always reserves the full size each time. And then there's actually industry standards for the length of a URL and an email address. And so I've seen people use max, varchar max for URL or email address. And that is a massive waste of time. Plus, you can't use the indexes. You can't index them, nor can you do comparisons that'll give you good search arguments. So this is a bad idea to use max. In all but a few cases, you really shouldn't be using max often. We see performance problems with any of the Unicode data types like nvarchar and nchar. That's because A, they are bigger. They're 4 bytes as opposed to 2 bytes for the standard text data types, but they also provoke some other problems. I'll show you that a little bit. I mentioned overstuffing. And by the way, Aaron Bertrand over at SQLperformance.com has a great blog post about how to do overstuffing well. If you've got to do it, how can you do that well? So look up JSON there, and he actually uses JSON and XML to kind of illustrate that. Really good stuff there. Also, I see all the time people have columns that are nullable, and then every time those columns are referenced, it has a is null function on it. It'll say, if this amount is null, make it 0. It's like, don't do that. make the column not null and set the default value to 0 so that it's always got a value in that. Part of the reason for that is because if you have a lot of values in there that are null, they won't be responsive to your index. They can't be searched by the index, right? So that's another problem. And then finally, we'll see that there are some data type choices that really destabilize what you're trying to do. For example, variables, parameters, columns that don't have the same data type in a stored procedure that references them as in the column itself. In fact, let's look at that a little bit more detail. That can cause two sorts of problems. One is you have to explicitly convert, right? So if you've got a data type that SQL Server doesn't know how to take care of itself, you got to explicitly convert them. But even worse than that is something called an implicit convert. And implicit conversion, as I show here, Jonathan Cahias wrote a great blog post about this. It can spike CPU like crazy when SQL Server doesn't expect to have to do a conversion on something that needs it. And that happens all the time because a lot of data types that look like they are compatible aren't actually compatible behind the scenes. So if you've got money or float or decimal and you say, is it equal to this integer value in a stored procedure, SQL Server behind the scenes has to do a cast or convert to switch it to the other data type. We'll see this with integers. And it's integer in a stored procedure and it's character in the or varchar in the table, or we see it between Unicode text fields and regular standard encoding for a char and a varchar. Let me actually switch over and show you that in the demo real quick. And gosh, we don't have a whole lot of time here. So let's say, for example, I've got a table here and my human resources employee table. And one developer references national ID number as if it was an integer. Another person puts it in quotes. And that's all it takes for SQL Server to say, oh, you mean that this is a text field of some kind. And then a third person does it as an in varchar or an in char. So let me turn on the actual execution plans. We'll execute this. And you can see it's taking a moment or two. And when we look at these, notice here the first one, it has to do a clustered index, an index scan here on the employee number field. And you can see in the pop-up down under the word predicate, it says convert implicit. It's because it doesn't know what's going on there. Again, in the middle one, we see an index seek, which means it can go right to the specific record it needs. And if we hover over that, we see that it doesn't have a convert implicit happening there. And then finally, in the last version, again, we also are able to avoid that. Now, if we do have implicit converts happening, I've also got a script here to show you those. You can look in the cache in a couple different ways. Here's one query from Penaldev over at SQL Authority. And this just looks at the whole server. It's just kind of quick and dirty. So it looks at everything and tells you where they occur. Another example, though, would be, and let me just show you this in a little bit more detail. I'm going to create a couple tables. Here I've got, in the product category, I've got a category ID that's an integer, but in the product table, I've got a category ID that's a varchar 10, okay? Those are not compatible data types. Now, SQL Server will not throw an error, but it will do some things that we don't want. And again, let's take a look here at these. We'll execute this. So they both return some information here, but if we look again, we can see that the second version here has got that clustered index scan. The first version here has a seek, but on the primary key of the second table, it's got a convert implicit. So this is going to cause you lots of problems. Anytime you see that convert implicit, it means that that particular table and that particular index isn't going to be used. So, it's a performance problem. Now, this other version of a query I mentioned to find these is by Jonathan Cahias, and it is database specific. Whoops. And let me run this. Now you can run this in production. It's safe. It won't harm anything, but it will look at all the data that you have in production, and it might take a few minutes to get through all of that. Okay. So this one will come back and tell me for the specific database how many and which queries are provoking a implicit conversion problem, and will let me know about that. See, and this is just a little database with, oh, I guess 4 gigabytes of RAM. So you can hazard a guess as to how long this query might take in a big production database with many gigabytes of RAM. So here it's telling me what that specific query is. All right. Okay, so let me move on here. There is a URL here for the kind of conversions that will provoke an implicit convert. So like date time to against, oh, I don't know, a big int or a timestamp will convert implicit, I'm sorry, will provoke implicit conversion. So this is a nice, useful little bit of information, and here's a link for you to download that. All right, now here's an interesting thing that a lot of people don't realize. When you design and lay out your SQL servers, you may have heard that anytime you declare foreign keys, you need to put a non-clustered index on those. Absolutely, positively true. You need to do that. Anywhere you have commonly referred to search arguments, like things you use in where clauses all the time, things you use in joins all the time, like a foreign key, absolutely do it. But what a lot of people don't realize is that you need to also declare foreign keys wherever you can. And I'll give you an explanation of that. A lot of people don't want to do it because they say referential integrity slows you down. There is a chance of that, but it will actually speed you up in a lot of cases too. And the reason for that is because SQL Server's optimization algorithm, it's looking for the optimal plan that it can apply, not the best plan. The difference between the best plan and the optimal plan is time. It might take 20 minutes to figure out the best plan, whereas the optimal plan, it wants to give you something that's good enough in just as little time as possible. So let's say we've got a 3-table join down here, or a 4-table join. We actually have 72 different physical access methods. And what we mean by that is things like ordered clustered index scan, unordered clustered index scan, and so forth. Lots of different ways we can physically get to the data. But then we can also have lots of different join orders of all these different tables, join A to B to D to C, and so forth. And then we have 3 different kinds of join algorithms it could use. That in fact actually ends up being 26,000 different plans it could choose from. So to get the very best plan, just in a 4-table join, is going to take a while. We don't want that. We want the optimal plan. And the way we get to the optimal plan is by doing some transformations. One is called simplification, and another one is called physical property enforcement that I will take a moment to explain. We're almost out of time, gosh. We're going to skip exploration and implementation. Don't have time for those. So you may know that when we're doing a execution plan, SQL Server goes through many steps. It binds, it parses, it binds, it simplifies the plan, then it loads the statistics, and then it applies some different heuristics from the engine before it gives you the final plan. The part we're talking about is simplification. Okay, so let me show you really quickly how SQL Server might do that. When we have a particular query, let me get a estimated execution plan on this one, okay? So here we've got 2 scans. It gives us a clustered index, non-clustered index warning saying we could create another index and we might get some better performance out of it, okay? Now, let's take a look at this one and also take a look at the execution plan here. So here it's broken it out. It's acting as if we don't have a subquery here. What it's done is it's simplified that into basically a join. Behind the scenes, SQL Server compresses that all down into as little access to the tables as it can manage. Then when it sees a situation where there might be a contradiction, like in this case, a unit price can't be both greater than 50 and less than 50. And there may be a check constraint that says that the unit price really can't be anything less than $10. So SQL Server will also, whoops, didn't get my estimated execution plan. It'll look at that and it'll say, you know what, I'm not even going to do a join there because I know I can't even access that because it's a contradiction. But when we have foreign keys, what SQL Server will do is it'll say that I'm going to remove that foreign key table entirely from the plan because the foreign key guarantees that the row has to exist. And so we're getting all of this stuff from the customer table, or the order header table, not from the customer table, and so we don't have to get any columns from it. And so in a case like this, we can do that kind of reduction or simplification because that foreign key exists. Oops, we don't have to even do that additional work there. Okay. And there's some other examples in here that show what happens if you change data, move things around. SQL Server will keep track of whether you dropped a clustered index and brought it back, and it'll tell you, hey, I can't do that because the data may be invalidated now. All right, so we're running out of time. And I hope to show you these different things as well, but we don't have time for that. A couple other things to discuss as well. Workload segregation. We see this happen all the time where people know about putting data files and their transaction logs on different files, perhaps on different parts of the storage subsystem. The very next thing you want to do, if you can, is you want to segregate your workloads out. Particularly if you have a reporting database or you have a read-heavy database, break that out. Make it a separate database. Give people separate access to that. Two reasons. One is earlier on I mentioned that every time you update a clustered index or insert to a clustered index or delete from it, you have to also, SQL Server behind the scenes has to update all the non-clustered indexes as well behind the scenes. And you don't want that on a very high throughput transaction processing system where you've also got every index you might need for reports. You might have 30, 40 indexes on a big table. Whereas if you have a reporting database that you're going to pull data out in all kinds of different ways, then set it up so that it gets loads on a regular basis from the transaction processing system, which has relatively few non-clustered indexes. While on the other hand, the reporting database has all that you need so that they don't encumber the OLTP database. Meanwhile, they speed up the reporting database. I guess the bottom line there is that a lot of people don't realize that your non-clustered indexes speed up reads, but they don't help with writes, and they can even slow down writes. So that's why you want to segregate these different workloads. Now I have a few more slides, but since we're running a little bit over, let me go ahead and stop and ask some questions before we go further. Kenneth, did you want to throw any of those questions out, or should I answer some of those?
Yeah, I can throw out some of the questions. So the one I really see here is, so should I create an additional index for each column rather than combining multiple columns into one index? Didn't realize there was a difference.
Well, of course, the true answer to every technology question is it depends, right? So many times, though, the answer is yes. The flip side is there are plenty of times where the answer is no. In a situation like that, what you might actually want is to take advantage of something called a covering index. And when you have a covering index, what that means is you always reference these two columns together. Oh, you like if you've ever been to a doctor's office, they always ask me my last name and my date of birth. Always asking for those together. If you put both of those into an index, that means the SQL Server doesn't even have to go down past the intermediate pages to get the data, right? Because they're stored in the intermediate pages. It doesn't have to, and so the query is covered by the index, and you don't have to go to the leaf pages, which might number in the millions. So that can save you time. On the other hand, if we do frequently query both by date of birth and separately by last name, then I should definitely create a non-clustered index on each of them. But as you're probably beginning to realize, Kirby, is that, boy, that's going to be a lot of indexes. And true, and most applications that have a ton of reports and stuff coming out of it, you are going to have maybe as many indexes as columns, maybe even more, to take advantage of the covering index principles. Because of that, that's why a lot of people are segregating their databases by workload. So the transaction-heavy database has relatively few non-clustered indexes because we want other people doing data entry to get their data in as fast as they can. On the other hand, we have all these reports coming out, and so we want to be able to query that data in every way imaginable. So we do want lots of non-clustered indexes there. And so that's the kind of thing in which, you know what, it's really going to help if I can have a read-only version, or maybe a read-mostly version of this database. And so you can do different things, like maybe use availability groups and do your reporting off of the secondary. Maybe you use replication or something like that to collect all the data on one server and do your reporting from there. There's a lot of ways to handle that. Now, some people have heard of included columns. That's another kind of index. The difference between an included column and a multi-column index that might be a covering index is added values. You create a included column, you add an additional value to. So you might say, create an index on last name and also include first name, but you're not making it part of the index. What that means is that first name is there with the last name index so that it can cover the data in the answer, but it is not part of the range of selectivity. Because one of the things that you want your indexes to do is offer you a lot of uniqueness in the records that you're looking at. And so when you use an included column, it doesn't do that extra step of adding to the selectivity and the statistical variation of the data. It only includes the data there on the intermediate pages so that it doesn't have to do that further lookup down on the leaf pages. Any other questions while we take a minute there?
I think that's it for questions, Kevin. The rest of everything in here looks like statements. Thank you very much. This was a very, very good presentation.
Well, folks, the bad news is that I still had a few slides to get through at the end. So what I would encourage you to do is, let me skip to the end here. Take a look at my blog. Actually, I don't have it listed here, but it's blogs.century1.com. And I'm going to, as soon as we get off the line here, I'm going to go ahead and create a blog post for this session. And if you check it later this afternoon or first thing tomorrow, I'll have all the slides and a whole bunch of scripts that I also didn't get time to show you. And some of them illustrate some of the principles. Some of the scripts actually help you find if there are any of these existing problems in your database. For example, you've got really oversized tables that are much, much bigger than they need to be, lots of varchar 300s in there or something. And you can also actually, this is kind of a cool thing we just added, you can text Kevin to 797979 and it'll give you a link to all my other slide decks. So this one is brand new. I just created it. It's not on that page, but if you want to see all the other stuff that I've done, then you can get all of those as well.
That's excellent.
All right.
And once Once I get it processed, I'll post the recording to YouTube, and I'll send that out with a link to your blog post as well to the group.
Fantastic. Thanks so much.
All right. Thank you very much, Kevin, and thank you everybody for joining us today. We'll see you in January.
Thanks. Bye-bye.